Hello friends, welcome back to my YouTube channel. In this 17th part of my discussion on liquid extraction, I will continue discussing stage-wise liquid extraction, but this time I will be discussing continuous counter-current multi-stage liquid extraction. So it is a continuous operation. It is carried out in a counter-current manner where the extract and raffinate phases, they are flowing counter current to each other and multiple stages are involved in it. So it is a continuous counter current multi-stage liquid extraction. So let us start the discussion. Okay, first of all, let us know about how stage-wise contact is used to carry out stage-wise liquid extraction operation. So stage-wise liquid extraction operation, in this case, the two insoluble liquid phases, they are contacted in a stage-wise manner. The two insoluble liquid phases that I am talking about, these are feed and solvent. So in stage-wise liquid extraction, feed and solvent, they are contacted with each other in a stage-wise manner. And this operation, the stage-wise liquid extraction, it is carried out in a stage-wise contact equipment, an equipment where there will be multiple stages in it. And each stage in this stage-wise contact equipment, it has provision for intimately mixing the two insoluble liquid phases, that is feed and solvent, and then the resulting mixture, when you mix feed and solvent, the resulting mixture will be settling into raffinate and extract phases. Therefore, there is also a provision to physically separate the resulting raffinate and extract phases from each other. So each stage has these two provisions: provision for intimately mixing feed and solvent and provision for physically separating the resulting raffinate and extract phases. Therefore, each stage, it is constituted of two equipment. One is the mixer and the other one is the settler. So you have a mixer which is followed by a settler, and combination of these two, it forms one stage. Then feed is admitted to this stage, solvent is admitted to this stage. These two will be first intimately mixed in the mixer. The resulting mixture will be then transferred to the settler, where it will be allowed to settle. It will settle into raffinate and extract phases, and then those raffinate and extract phases, they will be physically separated from each other. So in a single stage, there is mixing, and which is then followed by settling. So each stage will have these two equipment in it. Now, as per requirement, you can arrange multiple stages. The multiple stages in the stage-wise contact equipment, they can be arranged in a desired cascade. What is a cascade? Cascade of multiple stages. It is nothing but arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. So the stages are arranged in such a way that output from one stage, let us say this is stage number 1, output from stage number 1, it serves as input to stage number 2. So when you have this arrangement, we say that there is cascade of multiple stages. So cascade of multiple stages are arranged so that an output from one stage is input to the next stage. Two common cascades that are used to carry out stage-wise liquid extraction. One is cross current cascade, and then the other one is counter current cascade. So I have discussed cross current liquid extraction, cross current multi-stage liquid extraction in my earlier videos. I am giving link to the entire playlist of my videos on liquid extraction. You please watch all those videos So cross current cascade I have already discussed. Now today I'll be talking about, or I'll be discussing, counter current cascade. So when liquid extraction it is carried out in the counter current cascade, then you have multi-stage counter current liquid extraction. Multi-stage counter current liquid extraction. Multi-stage because there are multiple stages. Counter current because the raffinate and extract phases, they are flowing counter current to each other. So feed is admitted in the first stage. In this case, I'll shortly show the schematic diagram. So in this multi-stage counter current liquid extraction, feed is admitted in the first stage and solvent is admitted in the last stage. And then the raffinate and extract phases, they will flow from one stage to the other in a counter current manner. And since raffinate and extract phases, they are flowing in a counter current manner, this operation is called counter current liquid extraction. Multi-stage counter current liquid extraction. Another important thing is this operation is always carried out in a continuous manner. You cannot carry out this operation in a batch-wise manner. Multi-stage counter current liquid extraction will always be a continuous operation. And that's why the title that I have given to this discussion is continuous multi-stage counter current liquid extraction. It has to be carried out in a continuous manner where the raffinate phase will be continuously flowing and extract phase will be continuously flowing from one stage to the other, but they will be flowing in a counter current manner. Now let us consider a counter current liquid extraction which has n number of stages in it. So I'm calling it as n stage counter current liquid extraction. Counter current liquid extraction operation that is containing n number of stages. What ternary system we are considering in our discussion? The ternary system involved is A, B and C. C is the solute and therefore it is soluble in both A and B. A and B in this case, they are partially soluble in each other. In my last video, I had discussed the case where A and B, they were not at all soluble in each other. But that was cross current operation. Now, since I am discussing counter current liquid extraction operation, first I will consider the case where A and B, they are partially soluble in each other. And then I'll be, in my future videos, I'll be talking about the case where A and B, they are not at all soluble in each other. For now, for this video, we are considering A and B to be partially soluble in each other. And the feed solution in this case is solution of A and C, A plus C, where C is the solute to be recovered. The solvent is B if you are using pure solvent, and it would be B plus C plus A, where A and C, they will be present in a little amount. And when this is possible, when you are using a recovered solvent. So if you are using a recovered solvent, the solvent phase will have majority of B in it and little amount of C and A in it. And if you are using pure solvent, it will be just B in it. And in the feed solution and the solvent, they are contacted with each other in n stage counter current operation. And the operation will be continuous operation. The operation has to be a continuous operation. Now let me show the schematic diagram for this operation. So you have stage number 1, stage number 2, and then I'm considering any stage. I'm calling it as nth stage, and the last stage in this cascade is capital nth stage. So I have considered stage number 1, stage number 2, any stage which I have denoted by small n, and last stage in the cascade is capital nth stage. Now feed will be admitted to the first stage, and then it will be flowing from stage 1 to stage 2, and then it will be flowing from stage 2 to stage 3 and so on and so forth. So it will be flowing through stages that are shown in by these two lines. So within these two lines, you have many stages. Then uh, the solution will be coming out of n minus 1 stage, and that it will be going to nth stage. Then from the nth stage, again it will be flowing through a number of stages which are included in this between these two lines. And before going to the last stage, that is nth stage, it will be coming from capital N minus 1 stage. So feed, it is admitted to stage number 1, it will be flowing to stage number 2, it will be flowing to stage number 3, and then it will be flowing through nth stage, and then it will again be flowing through many other stages before entering the final stage in the cascade, which is capital Nth stage. Solvent, and then it will come out of the nth stage, the last stage in the cascade. So this will be the final raffinate that is obtained in this operation. Whereas the solvent will be entering the last stage, and then it will be flowing through a number of stages that are included in this between these two lines, and then it will be coming to nth stage. From nth stage, it will again flow through a number of stages that are included in this between these two lines, and then it will be coming to stage number 2, then from stage number 2 to stage number 1, and finally it will be coming out of stage number 1, and it will be the final extract phase that is obtained in this operation. So now the feed solution that comes out, the raffinate phase that comes out of stage number 1, then raffinate phase that comes out of stage number 2, raffinate phase that is coming out of n minus 1 stage. This is a raffinate phase that is coming out of n stage. This is a raffinate phase that is coming out of capital N minus 1 stage, and finally you have the final raffinate. Then you have the extract phase that is coming out of nth stage. Then you have the extract phase that is coming out of small n plus 1 stage, and then going into the n stage. And from n stage you have the extract phase coming out. Then in between nth and second stage there are many other stages. So before entering stage number 2, we will be having extract phase that has come out of stage number 3. Then from stage number 2, extract phase will be coming out, and it will be going to stage number 1, and from stage number 1, finally it will be coming out as the final extract phase. Now talk about the notations that I have used over here. I have not told you earlier, I didn't tell you what are these notations. Now let me tell you. Feed solution, in this case F is the mass flow rate. It will be mass flow rate because it is a continuous operation. Then XF is weight fraction of C in the feed. C is the solute to be recovered. Then solvent, for solvent you have Sn plus 1, which is the mass flow rate, the rate at which solvent is entering in the last stage. Since it is coming from a stage which is next to stage number, the last stage, that is capital N stage. So I have denoted it as solvent that is coming from N plus 1 stage. So the notation tells you from where the solvent is coming. Now since there is no any stage after nth stage, I have considered an imaginary stage, and that stage is N plus 1 stage. So the fresh solvent that is admitted to N stage, we are considering it to be coming from an imaginary stage. And what is the number of that imaginary stage? It is N plus 1. So N plus 1 is the mass flow rate. Why N plus 1 is weight fraction of C, weight fraction of solute in this solvent. Then raffinate phase, all raffinate phase, they will be denoted by capital R. The mass flow rate will be denoted by capital R. So the number tells you this, the number signifies the stage from which it is coming out. For example, if it is R1, that means this raffinate phase is coming out of stage number 1. If it is R2, this raffinate phase is coming out of stage number 2, so on and so forth. So in general, if it is coming out of Rn would be the raffinate phase, mass flow rate of the raffinate phase that is coming out of nth stage. So likewise, the final raffinate phase, the mass flow rate is Rn, and it is the raffinate phase that is coming out of the last stage, which is capital nth stage. Then X is weight fraction of solute in those raffinate phases. So you have different, depending on the number of the stage from which the raffinate phase comes out. You have X1, X2, X3, Xn, X capital N, the final composition of the raffinate phase. So X represent weight fraction of the C, weight fraction of the solute. Sorry. Then solvent, in this case, the extract phase. Extract phase, you have E will be its mass flow rates, and then extract phase coming out of different stages will have different mass flow rates. So En, E capital N is mass flow rate of the extract phase that is coming out of N stage. E small n is the mass flow rate of the extract phase that is coming out of small n stage. E2 is the mass flow rate of extract phase that is coming out of stage number 2. And final extract phase, which comes out of stage number 1, it will be having a mass flow rate of E1. And small y will be weight fraction of C in those extract phases, weight fraction of the solute. So this is how you can represent the n stage countercurrent liquid extraction operation with the help of a schematic diagram. Okay, now we will consider the entire cascade, which will have all the stages in it. So I am covering those stages by an envelope, this red envelope. Now I will be taking steady state total material balance for this envelope. So it would be F, input is equal to output, steady state. So it would be F plus Sn plus 1, that is feed flow rate plus solvent flow rate. First, a mixture will be formed in the entire cascade, and then this mixture will be separated. The mixture that is formed in different stages in the cascade, I am denoting it by the mass flow rate of that mixture. I am denoting it by M, and then this mixture, the imaginary mixture that forms, because M represents the mass flow rate of the mixture for the entire cascade, and then it will be separating into raffinate phase that is coming out of nth stage, the last stage, and extract phase that comes out of the first stage. So steady state total material balance for the entire cascade will be written in this way: feed plus solvent is equal to mixture, which then settles into raffinate and extract phase. So the equation is F plus Sn plus 1, that is equal to M, that is equal to Rn plus E1, and I am calling this as equation number 1. Then let us write steady state material balance for the solute. So it will be written as F into XF, that is total feed into fraction of C in it. So F into XF plus N plus Sn plus 1 into Yn plus 1, that is equal to M into Xm, where Xm is the weight fraction of the solute in the mixture that is formed in the entire cascade, and then it separates into raffinate. It will be Rn into Xn, R capital N into X capital N plus E1 into Y1, and I am calling this as equation number 2. So now we can write it like this. Now I have written the equation so that I have quantities. On the left hand side, I have quantities that are known to me. So it will be F into Xf plus Sn plus 1 into Yn plus 1, that is equal to M into Xm. So now I am considering the equation where on the left hand side, all quantities are known to me. Okay. So from this equation, Xm will be equal to Fxf plus Sn plus 1 into Yn plus 1 divided by M. So that means equation number 3, which this is equation number 3. Equation number 3 I can use to find out Xm. which I will need for my calculations. So from the steady state material balance for the solid, I am getting equation for Xm and calling it as equation number 3. Now I will use equation number 1 to replace m with f plus Sn plus 1, because m, as per equation number 1, it is equal to f plus Sn plus 1. So we got equation 3, which is Xm is equal to f into Xf plus Sn plus 1 into Yn plus 1 divided by m. But according to equation 1, f plus Sn plus 1 is equal to m, that is equal to Rn plus E1, that is m is equal to f plus Sn plus 1. F is known, Sn plus is known, I can get m. That means I can replace m in equation number 3 with this equation. So using in equation 3, if I use this in equation 3, Xm will be equal to Fxf plus Sn plus 1 into Yn plus 1 divided by f plus Sn plus 1. Now everything on the right hand side of this equation is known and you can get the value of Xn. That is the use of this equation. This equation is used to find out Xm, which will be further used in our analysis. Now equation 1, you can arrange it in a different way. So this is equation number 1. Now I will arrange it like this. F minus E1, that is the equation is, let me write over here. Equation is F plus Sn plus 1 is equal to Rn plus E1, equation 1. Now this is arranged in this way. So this E1 is brought on this side, so it is F minus E1, and that is equal to Rn minus Sn plus 1. And this difference, I am denoting it by delta R. F minus E1, which is equal to Rn minus Sn plus 1, that is equal to delta R. So delta R in this case is called the reference point. It is called the reference point because it gives difference in flow rates at the respective rates. For example, F minus E1 is difference in the flow rate, net flow rate in the right direction. Similarly, Rn minus Sn plus 1. So this gives the net flow out of the operation, net flow out of the cascade. So since it is giving difference in the flow rates at the two ends, this is called difference point. Delta R is called the reference point. It gives net material flow out of nth stage. It gives net material flow out of nth stage. So if you consider this end, the difference Rn minus Sn plus 1, it gives net material flow out of nth stage. Now delta R, it remains constant between any two adjacent stages. So we are going to show this. The statement is delta R, that is difference in flow rate. Difference in flow rate, it remains constant or it is same between any two adjacent stages. So in order to prove this, I am going to consider some stages. Which stages? From nth stage to the last stage, capital N stage. So I am considering stages from nth stage, any stage which is small n stage, to the last stage which is capital Nth stage. So now I will draw an envelope around the portion of the cascade that I have considered. And if I write steady state total material balance for this green envelope, then it will be written as Rn minus 1 plus Sn plus 1, that is equal to m n, the mixture that will be formed within that envelope, which will then separate into Rn plus En. The raffinate phase and the extract phase. Raffinate phase is coming out of the last stage, that is capital N stage, and extract phase is coming out from any nth stage, small nth stage. If I rearrange it, I will write it in this way: Rn minus 1 minus En is equal to Rn, R capital N minus Sn plus 1. And now I'm calling it as equation 5. So this equation, it is transformed into a form that is represented in equation 5. Rn minus 1 minus En. So Rn minus 1 minus En is the difference in the material flow between n minus 1 stage and n stage. And this is equal to difference in the flow rate, difference in the material flow at the end, net material flow out of the cascade. So equation 4 was F minus E1 is equal to Rn minus Sn plus 1. That is Rn minus Sn plus 1 is nothing but delta R, which suggests that if you use equation 4 in equation 5, you can get R small n minus 1 minus E small n, that is equal to delta R. That is difference in flow between any two adjacent stages. It is delta R. So thus we have proved that delta R is constant between any two adjacent stages in the cascade. Okay, now we will follow the material balances that we have written from equation 1 to equation 5. We will follow these equations on the ternary diagram. And the ternary diagram that I am drawing is, I will be plotting nx and ny on x-axis. I will tell you what are this nx and ny, and then small x and small y I will be plotting on the y-axis. So in this case, nx is weight fraction of B in the raffinate phase, ny is weight fraction of B in the extract phase, x, small x is weight fraction of C in the raffinate phase, small y is weight fraction of C in the extract phase. And what are you going to do, or what we will do? Nx we will plot against x, and if I do that, if nx is plotted against x, we will get the A reach part of the binodal solubility curve. And when you plot ny against corresponding y, you will be getting the B reach part of the binodal solubility curve. So in this way, you have the ternary equilibrium diagram, which we will use, or we will follow all the material balance equations that we have written on this ternary equilibrium diagram. So let me take the diagram over here. First is we will be locating point F. Point F, it will be located at a point which has coordinates of 0, xf. That means this point will be located on the y-axis, where x is equal to xf. So this is x is equal to xf, and at this point F will be located. Then we have to locate the point Sn plus 1. The next task is location of point Sn plus 1. Sn plus 1 will be located at a point which has coordinates of nys, ys, where nys is weight fraction of B in the solvent phase. And if you are using pure solvent, then ys will be 0, because there will be no solute in it. There will be just B in it. And if it is only B in it, its weight fraction will be 1. That is, nys will be equal to 1. So in that case, S will be located at a point which has coordinates of 1, 0, because it is just B. Therefore, nys will be equal to 1. There is no C in it for pure solvent. Therefore, ys is 0. So coordinate of the point Sn plus 1, in this case, it will be 1, 0. So point S will be located at the point which has coordinates of 1, 0. Point S is located. So let us say that we are using a reuse. If a recovered solvent is used, then there will be some value of ys in it. So ys, and there will be some value for nys, and then point S will be located with this coordinates ys and nys. And then we have to connect points F and Sn plus 1. After locating point Sn plus 1, we have to connect those 2 points F and Sn plus 1 by a straight line. So I am doing that. So after locating point point F and then Sn plus 1, we have to connect the 2 points, point F and point Sn plus 1, which we will be using in our calculations. Okay, now let us move ahead. Now let us locate point M. Point M will be located with coordinates Nm and Xm. In this case, Nm is weight fraction of B in the mixture that will be formed in the cascade, and Xm is weight fraction of C in the mixture, So we are going to use Xm to locate point M. So Xm, it will be located on the y-axis, and after locating it, I will go to the line Fs, and where the intersection occurs, that intersection point will be nothing but point M. So in this way, you have to locate point M. Next is you have to locate point Rn. Point Rn, it will be located with this coordinates Nn and Xn. What is Nn? Nn is weight fraction of B in the final raffinate, and Xn is weight fraction of C in the final raffinate. And over here, we are going to use the value of Xn. So after locating Xn, I will go to the A-reach part of the binodal solubility curve. So wherever I get the point, I am calling that point as Rn. So in this way, you have to locate point Rn. Then after locating point Rn, what we will do, we will draw a line through Rn, and we will draw a straight line that starts from point Rn, passes through M, and then I will allow it to intersect the binodal solubility curve. And wherever intersection occurs, I will call that point as point E1. So from Rn, I will draw a line that passes through M, and then which intersects on the B-reach part of the binodal solubility curve. And now I am calling this point as point E1. I am calling this point as point E1. Okay, so now we have to locate point delta R. So for that, I will draw a line that starts from Sn plus 1, passes through Rn, and then I will extend it for some distance. Then I will draw a line that starts from point E1, passes through F, and allow it to intersect through the line, intersect with the line that I have drawn previously. So the intersection point is nothing but the point delta R. So starting from Sn plus 1, I will draw a line that passes through Rn, extend it for some distance in this way. Then starting from point E1, I will draw a straight line, allow it to pass through F, and then extend it so that I get an intersection with the first line that was drawn, and this intersection point is nothing but the point delta R, the reference point. Intersection delta R is nothing but, or the intersection point is delta R, the reference point, which we were to locate. So now in this way, you can locate point delta R. Next is the important task. Let us learn how to find number of stages. So for finding number of stages, we will make use of this diagram, the ternary diagram. We will also make use, or we will also need the distribution diagram. What is the distribution diagram? Distribution diagram is obtained when you plot x, small x, weight fraction of C in the raffinate on the x-axis, and small y, weight fraction of C in the extract phase on y-axis. You get the distribution curve. So we will be using the distribution diagram, and the ternary diagram to find the number of stages. Now in this case, we are going to get the number of equilibrium stages, number of ideal stages, or number of theoretical stages. So these are equilibrium stages, number of equilibrium stages. So let us understand. So first thing is, now I have got point E1. I will read its y coordinate. I will read the y coordinate of point E1, and that will let me call that coordinate, the coordinate that I get, y coordinate for point E1, let me call it as small y1. So with this small y1, I will go to the distribution diagram, locate it on the y-axis where small y are plotted. So for this small y1, with the help of the distribution diagram, I will find small x1 that is in equilibrium with small y1. So for that, from y1, I will go to the equilibrium curve and then go to the x-axis, which will give me x1. Okay, so I have found out x1, which is in equilibrium with y1. Now this x1, I will locate on the A reach part of the binodal solubility curve, and with the help of this x1, I'll be locating a point on the A reach part of the binodal solubility curve, and I'll be calling that point as R1. So here I'm locating it with x1. I will read it on the y-axis. Then I will go to the A reach part of the binodal solubility curve. Wherever intersection occurs, I will call that point as R1. Okay? So R1 and E1, they are in equilibrium with each other because R1 is located with the help of x1. E1 is located with the help of y1s, and x1 and y1, they are in equilibrium with each other. That means these 2 points, they are representing concentrations that are in equilibrium with each other. Therefore, these 2 points must be connected by a tie line. So this green line represents a tie line that is connecting R1 and E1. Composition at R1 is x1, composition at E1 is y1, and x1 and y1, they are in equilibrium with each other. Then next, when I get R1, I will draw a line that starts from delta R, passes through R1, and then intersects the B reach part of the binodal solubility curve. So I will start at delta R, then pass through R1, and then reach the B reach binodal solubility curve. Where the intersection occurs, I am going to call that point as point E2. So once point E2 is located, I will read its y coordinate. I will call it as y2. I will take this y2, come to the distribution diagram, locate y2 on it, then I will go to the equilibrium curve and get the corresponding value of x2. I will pick up this x2, again come to the ternary diagram, locate x2 on the y-axis, go to the A reach part of the binodal solubility curve where intersection occurs. I will call that point as R2 because I have got this point with the help of x2. And since x2 and y2, they are in equilibrium with each other, point with coordinate x2 and point with coordinate y2, they will be connected by a tie line. So you have another tie line that connects R2 and E2. Next, when I get R2, point R2, now I will be drawing a line from delta R, allow it to pass through R2, and then I will extend it to the B reach part of the binodal solubility curve. So if I do that, I will get this line, I will get this point. Now I am calling this point as E3, and for E3, I will read corresponding Y3. With this Y3, I will come back to the distribution diagram, I will locate Y3 on it, and then go to the equilibrium curve, and then find out corresponding X3. Then I use this X3 and locate R3. So X3 on the y-axis, then I'll go to the A reach part of the curve where intersection occurs. That will give me point R3. So now R3, since X3 and Y3, they are in equilibrium with each other, they will be connected by a tie line. Next, I will draw a line from delta R, allow it to pass through R3, and then the intersection with the B reach part of the curve, the point is E4. I will read corresponding Y4 on the y-axis. I will come back to the distribution diagram. I will locate Y4 and get corresponding X4. I will get corresponding X4. Okay. Then I'll use this X4, come back to the ternary diagram, and then I'll locate point R4. R4 is located with the help of X4. Since X4 and Y4, they are in equilibrium with each other, they will be connected by a tie line. Next is, I will have to draw a line from delta R, allow it to pass through R4, and then get E5 on the B reach part of the curve. So I draw a line from delta R, allow it to pass through R4, then the point where it intersects the B reach part of the curve, that point I will call E5. I will read corresponding Y5. I'll come back to the distribution diagram, locate Y5 on it, and then get the corresponding value of X5. Then with the help of this X5, I'll come back to the ternary diagram. I will locate it on the y-axis, then come back to the A reach part of the curve. I will locate R5 point with the help of the value of X5. Now, since X5 and Y5, they are in equilibrium with each other, points R5 and E5, they will be connected by a tie line. Then next, I'll have to draw a line that starts from delta R, passes through R5 and intersects the B reach part of the curve. So in that process, I get point E5. In that process, I get the point which I am calling as E6, and then I will read corresponding Y6. I will come back to the distribution diagram. I will locate Y6. I will find corresponding X6, and then with this X6, I am going to locate R6 as I had done in the previous cases. And then since R6 and E6, they are in equilibrium with each other, I will have to connect them with the help of this green tie line. In the process, R6, when I get R6, I have crossed Rn. Now R6 is less than Rn. So now I will have to stop. So I will have to continue doing this till Rn is crossed. Once Rn is crossed, your process stops, your procedure ends. And what you have to do, you just have to count the number of tie lines that you have drawn in the process. 1, 2, 3, 4, 5, and 6. So in this operation, each tie line will represent an equilibrium stage. So that's why the number of tie lines drawn in this case, that will be the number of equilibrium stages for this operation. So in this way, you have to find number of equilibrium stages in the counter current liquid extraction operation. So for that, you need to use the ternary diagram and you need to use the distribution diagram. I hope you have learned. I hope you have understood how to get those number of stages. If you have any doubts, you please mention them in the comment section. Okay, the next thing, let us say we have this thing. Now, what happens if you increase the amount of solvent that you use in the operation? So, if you increase the amount of solvent, what happens? This point M moves towards Sn plus 1. So, point M, it moves towards Sn plus 1 along this line. And delta R, it moves further to the left. So delta R will be moving further to the left. And when this happens if you increase the amount of solvent in the operation. If you further increase the amount of solvent, what is going to happen? Lines Sn plus 1 Rn, that is this line, Sn plus 1 Rn, this line, and the line even F, the first and the last line, they will become parallel to each other. If you till, and if it becomes parallel, if this line and this line, they become parallel to each other, this delta r, it will be located at an infinite distance. So in that case, delta r is located at an infinite distance on the left. If you increase the solvent, a further increase in the amount of solvent, what is going to happen? This intersection is going to occur on the right hand side. So now you are increasing the solvent. Now stage is reached, the two lines, this last two lines, now they are parallel. When you further increase the solvent, these two lines will intersect on the right hand side of this ternary diagram. A further increase in the amount of solvent, it will cause the line Sn plus 1 Rn and even F to intersect on the right side of the diagram. Okay, there is another concept which is minimum amount of solvent. How to get it? Let us understand. So we'll understand with the help of this diagram. So when a line from delta R, that is this blue lines, any blue line that originates at delta R coincides with the tie line, that is the blue line and green line, they coincide with each other, then we will need an infinite number of stages in the operation. An infinite number of stages will be required in the operation. Then the maximum amount of solvent for which this occurs, what occurs? You have infinite number of stages. When this happens, when line from delta R coincides with a tie line, then the maximum amount of solvent for which this occurs, it corresponds to minimum solvent to feed ratio that can be used. It corresponds to minimum solvent to feed ratio that can be used. So when this is possible, when a line that originates from delta R, that is this blue line, it coincides with the tie line, that is the green line. How to find the minimum amount of solvent? Let us understand. So you need to draw, a tie line is drawn that passes through point F. So we are supposed to draw a tie line that passes through point F. Again, we have to draw it by trial and error, and for that we will have to make use of the distribution diagram. In my next video, I'll be discussing a numerical where I'll tell you how to find the minimum amount of solvent. So we need to draw a tie line that passes through point F, and it will be drawn by a trial and error procedure, and for that we will be using the distribution diagram. So it is extended, the tie line that you have drawn, it is extended so that it intersects the line Sn plus 1 Rn at delta R minimum. So I'll draw a tie line. The black color line is the tie line that is passing through F, and it is intersecting the line Sn plus 1 Rn, and the intersection point is nothing but delta R corresponding to minimum amount of solvent, and I'm calling it as delta R minimum. Okay, so now we will use delta R minimum to find out the minimum amount of solvent. But before that, let me tell you, the end point of the tie line on B reach binodal solubility curve is E1 minimum. So this end point, we will be denoting it as E1 minimum, and we are going to use it in our calculations. Okay, now I am just showing the tie line that I have drawn through F, and then I have got E1 minimum. Next is what I will do, I will connect E1 minimum with Rn. So I will connect E1 minimum with Rn. So in this process, I will get this point, a point where intersection of E1 minimum Rn with Fn plus 1 occurs. So this point is m corresponding to minimum amount of solvent. I am calling it as m minimum. ठीक है. Then for this m minimum, I will get x m minimum. I go to the y-axis and get xm minimum. We know equation for xm is fxf plus sn plus 1 into yn plus 1 divided by f plus sn plus 1. And if xm becomes xm minimum, sn plus 1 will be s minimum. So fxf plus s minimum into yn plus 1 divided by f plus s minimum. So with the help of this equation, everything is known to you. Only s minimum is not known. You can solve this and get the value of s minimum. So in this way, you can find out the minimum amount of solvent. Okay, the last thing that I'll do today is I will compare counter current liquid extraction with cross current liquid extraction. So for a given degree of separation and a given amount of solvent, if you want to have fixed separation with fixed amount of solvent, then counter current liquid extraction, it will require lesser number of stages. And for a fixed number of stages, if you are using the same number of stages in both the operations, the amount of solvent required in counter current operation, it will be lesser. Counter current liquid extraction requires a lesser amount of solvent. So for a given degree of separation and for a given amount of solvent, number of stages are lesser in counter current operation. Then for a fixed number of stages, amount of solvent is lesser in counter current liquid extraction. So in this way, you can remember the difference. You can remember the comparison between cross current and counter current liquid extraction operations. So with this, I end my discussion for this video. Here, I hope you must have learned how to find out number of equilibrium stages in a continuous multi-stage counter current liquid extraction operation. In my next video, I will be solving a numerical where we will be finding number of equilibrium stages. But for this video, let me stop. I hope you have understood the concepts that I have discussed in this video. If you have any doubts, you please let me know in the comment section. Thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to my channel. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Thank you. Have a nice day and hope to see you soon in my next video.